Here we are in our last video of the course. Crazy. Anyways, let's talk about partial derivatives. So this is really going to depend on understanding how a multivariable function works. So I'll try and reiterate a couple of things, but if you get confused with how these variables are interacting with each other, try and go back to the multivariable function video and see if you can't pick some stuff up now that you see where we're going to use this. So I know I didn't touch on a lot of the specific things in the text for that video, but I think I set us up for what we need here. So go back if you need to, because this can be a little bit confusing at first, but once we figure out that relationship between variables, this section, this topic is actually going to be a pretty short one. So here we go. We know we're talking about multivariable functions, and this is a big deal here. X and Y are going to be independent variables, meaning if we change X, Y doesn't necessarily change. They act independently of each other. We're going to call our output variable, our dependent variable, Z. And so if we change X, Z will change. And if we change Y, Z will change. And that's the relationship. X and Y act independent of each other, but they both impact our output variable, Z. So what we'll say is that they're constant with regard to each other. When X changes, Y stays the same. So it's kind of like a constant, just like if X changes, 3 stays 3. And you'll see more about what I mean when we get into that. Let's talk about partial derivatives. This is some weird notation. This seems a little bit weird, but I promise it's not. So we're going to talk about partial derivatives. We're going to talk about a derivative with respect to X and with respect to Y, and this is what it looks like. So first off, we have to determine which one is going to act like the variable, which one is going to be the one that changes. When we have a partial derivative with respect to X, we write a little subscript X. When we have a partial derivative with respect to Y, we write a little subscript Y. We can't just use this prime notation because we have to denote which of the X and Y independent variables we're talking about. So when we talk about a partial derivative with respect to X, we use F with a little X. Sometimes I'll just leave it like this and I won't even write the little function variable notation. We'll just write F subscript X. Our differential notation has changed. We still have something that kind of looks like a D over a dx. This is dz, I guess, where z is our output variable. But really, this here, oops, I completely missed that. This here is the Greek letter delta. It means something very similar to like dy over dx, where that's the derivative of y, where x is the variable. This only means partial derivative. So when you see these little deltas now, that's really indicating the fact that this is a multivariable function, and so we're looking at a partial derivative. Really, you're going to find that it's not much of a big deal. We won't use this notation much. We'll mostly use stuff like this. Notice that if we define this as a limit, which you can mess around with a little bit if you want. When we talk about the derivative with regard to x, x is the variable that gets the plus h. And so we have the limit as h goes to 0 of f of x plus h and then y minus f of x and then y. Notice y didn't change here. Only the x variable did, and we still divide it by h. When we have the partial derivative with respect to y, we do the same thing, but now we have the y variable as being the one that gets that plus h on there. So y is the variable that's changing in this difference quotient. X is staying the same now. We're not going to work a ton with that definition because I think if we jump into an example, we can kind of see what's going on pretty quickly. Just keep in mind the fact that when we're looking at a partial derivative with regard to x, y is not changing. All right, here's an example. Let's find the two partial derivatives here. Maybe I'll do the partial derivative with regard to x in blue, and I can do the partial derivative with regard to y in red. Let's start with this one. We're going to look at each term, and we're going to take a derivative the way that we normally would, but notice there's x's and y's here. We're not going to use implicit differentiation or anything like that because both x and y are independent variables. That's really the key that we're going to keep coming back to. What that means is that when x changes, y doesn't, and when y changes, x doesn't. When we look at a partial derivative with regard to x, x is the variable that's changing. So we're going to treat x like a variable, and y is going to act like a number, like a constant. It's just going to be fixed. So this term is pretty much going to be the same as we always would expect it to be. The derivative is going to be 4x. No surprises there. Maybe I'll go to the end, and we'll say the derivative of 1 is definitely going to be 0 still. Now, these two terms are a little bit strange. Let's talk first about 5y. The derivative of 5y with regard to x is not going to be 5, and it's not going to be 5y prime or anything like that. What we're going to notice is that if y is an independent variable, that means it doesn't change. That means it's fixed. It acts just like a number. So it's possible that y is just 1 in this case, or y is just 7, or y is some other y value, but it just stays there. If y is just some fixed number, then 5 times y is also going to be some fixed number. We don't know what it is, but it's a constant. So the derivative of that is also going to be 0. Following? It's a little bit weird. Oh well. All right, now let's talk about this middle term. Here, y is just a number, but so is 3. So let's first cover up y and see what would be the derivative of 3x squared, or I guess negative 3x squared. We'd say negative 6x, right? The reason is that really we have 3 times the derivative of x squared, which is 2x. So if we go back and say, wait a second, there's a y in there, but y is just acting like a regular number, that means that not only does 3 stick around, and we multiply by the derivative of x, but y sticks around too. It's a part of the coefficient just like 3 is. It's acting like a number, and so it just sticks around. Essentially, we just look at the x squared part and take the derivative of that. So our derivative of negative 3x squared y is going to be negative 6xy. So our partial derivative, 4x minus 6xy. That's our partial derivative with regard to x. All right, pause this a second. See if you can figure out the partial derivative with respect to y. It's going to be a little bit different, but oh well. All right, here we go. So we're going to first look at 2x squared. Notice there's no y's in that. So x is just going to be some fixed number. So this thing here is constant. So the derivative of that is 0. Now we've got this 3x squared y term. Now y is the thing that we're taking a derivative of. If we scratch out the x squared and pretend that this was just negative 3y, then the derivative would just be 3. But the problem is there's that x squared in there as well. And so when we take the derivative of y, or the stuff with y, maybe I'll say the coefficient on y, just the coefficient is left over. Y goes away. You could think there's a little exponent of 1 on here that we brought out front and then we subtracted 1. So we end up with negative 3x squared times 1 times y to the 0. So we end up with just negative 3x squared. Then we've got this plus 5y. The derivative is just going to be 5. Again, not 5y prime, because y is an independent variable. So it's acting like the variable here. And 1 is still a constant, so we end up with 0. Negative 3x squared plus 5. That is your partial derivative with regard to y. So I think really the hardest part is this kind of term where there's things mixed. We'll get used to it pretty quickly when the 5y term goes to 0 when we're looking at the partial derivative with regard to x, and when the 2x squared term goes to 0 when we're looking at the partial derivative with y. They don't have the variable that we care about in there, so they're constant. People typically mix up the stuff with the coefficient where there's a mixture of those things. Let's take a look at this one. Maybe first we can rewrite this and say, all right, our function is really x natural log y, oops, sorry, that's supposed to be minus 4x cubed y squared, and I could change this to x y to the negative 1 if you want. That might make it a little bit easier. But again, what we're going to do is find a partial derivative with regard to x, and we're going to find a partial derivative with regard to y. Try and take a second, see if you can figure out what's going on here. All of these are mixed terms. So when we're looking at x here, we're just going to leave the y stuff alone because it's going to be kind of like a coefficient. When we're doing the y stuff over here, we're going to leave the x stuff alone because it's going to be part of the coefficient. Pause the video, see if you can figure it out. All right, so this first term, if we're looking at it with regard to x, we're going to say the natural log y is just a coefficient. So the x goes away and we're just left with natural log y. Here we're going to bring our exponent down. So we end up with 12x squared, and our y squared sticks around because it's a part of the coefficient. And this is like a linear term for x, and so we just end up with y to the negative 1. So you've got the natural log of y minus 12x squared y squared plus 1 over y. That is your partial derivative with regard to x. And your partial derivative with regard to y, x is going to be a coefficient. It's just a number here. So we're going to look at the derivative of the natural log of y. That's going to be 1 over y, but we got to multiply it by x. So we end up with x over y. Here we're going to do the power rule. We're going to bring this out front and subtract 1. So we end up with negative 8x cubed times y. And here we've got to do the same thing. Bring this out front and subtract 1. So this is minus xy to the negative 2. Or we can say x over y minus 8x cubed y minus x over y squared. That's your partial derivative with regard to y. We got one more here. I'm going to give you a hint before you stop and do this. There's some chain rule going on. So the outside derivative is going to be the same for both of these things. When you find the partial derivative with regard to x and when you find the partial derivative with regard to y, they're both going to start out identically, where the 5 is going to come out front of the box and we're going to subtract 1. So on both of these, you're going to end up with 5 times your box raised to the 4 but then when you multiply by box prime, that's going to be a bit different. This is going to be like box prime with regard to x, and over here you're going to have a box prime with regard to y. So they're going to be a little bit different from each other. So figure that out. All right, if you've got it, we'll see what we've got here. 5x squared plus 2xy to the 4, and now we take the derivative of this inside stuff with x as the variable. So we've got 2x plus 2y here. And in this case, we can do some distributive property if you want. Here, we could say 10x plus 10y times x squared plus 2xy to the 4. And that's about as good as we get. In this one, we've got 5 times x squared plus 2xy to the 4. But now, when we take the derivative of the inside where y is the variable, this first term is constant, so that's going to be a 0. And the second term is a linear function with regard to y, so we'll just say 2x. So on this one, we end up with 10x times x squared plus 2xy to the 4. And I think you could pretty much leave both of these this way. So here, when we're doing the chain rule, only these box primes are impacted by the partial derivative stuff, because the derivative of the outside is still going to end up being this whole box to the 5th thing. So we're going to still bring the 5 out front and subtract 1. That arrow is supposed to point out front of the box. There we go. And subtract 1. So we're going to end up with 5 times our box raised to the 4th in both of these things. So same thing is going to happen when you do the product rule. Whenever you set up your u's and v's, your u primes and v primes are now going to be partial derivatives with regard to whatever variable you're looking at. Same thing with the quotient rule. There's a bunch of examples of those, but I'll give you a hint. We don't really need to worry too much about some of these bigger derivative rules. We might see a small chain rule or maybe a small product rule. If you get comfortable with the basics of those things, you'll be good. All right, here's the question then. In our class, we looked at derivatives, and then we quickly moved on to second derivatives. What about our second derivatives here? Well, if we have a function, and this is the function that we dealt with earlier, so just as a reminder, did I use blue for x or red? Let me remind myself. Okay, blue. Here we had f sub x, and that was 4x minus 6xy. And we had the partial derivative with regard to y that was minus 3x squared plus 5. This is the same example that we did right at the very beginning. We're going to call this our first order partial derivatives. These are essentially first derivatives. We have two of them, though. Now, if we want to find a second derivative, we're going to do it the exact same way that we did before. A second derivative is going to be the derivative of the derivative. But now, since we have two options at each, we can find the derivative of this with regard to x. We're going to call it fxx. Or we can find the derivative of this with regard to y. So we're going to call that fxy. Notice the subscripts now just give you the order of which you took derivatives. First, we took a derivative with regard to x. Then we took another derivative of that thing with regard to x. So here, find the derivative of that with regard to x. And then if you want, fill in the partial derivative with regard to y. See what you get. All right, we should get 4 minus 6y here. Both of those are linear with regard to x. Cool. And here, we're going to say this is constant with regard to y, and so we end up with negative 6x here. Now, for the other one, we get two options again. fyx, we take a derivative of this with regard to x. That's negative 6x. And we get one more option. Oops, I meant to switch that to red. There we go. fyy, and the derivative of that's going to be 0. There's no y terms here. So basically, we're doing the exact same thing, except we're saying both of these started with fy, and both of these ones started with fx, because that's the partial derivative it came from. So on an exam, I might ask you to say, find fxy, and you'll look at this and say, all right, x first, then y after that. So you're going to do 2 rounds of derivatives, and you're just going to look at the order of this little subscript to tell you kind of the recipe for how to find that. So we could do third order derivatives where I just put another x here, and you'll say, okay, x, then I'll take a derivative of that with regard to y, then I'll take a derivative of that with regard to x. We could do this a whole bunch of times, but really we only did up to second derivatives, and so that's what we're going to do as well. So these we'll say are our second order partial derivatives because we did 2 rounds of differentiation to get them. Notice for me, I'm going to use, maybe I'll use orange for our last thing, or gray. Here's a good color, gray. Notice these two things are the same. The question that I normally pose to our classes is that always going to be the case? And if we were in a face-to-face class right at the end of the semester, we maybe would have a bit of extra time. And so sometimes what I'll do is I'll put a couple of different functions up on the board, and I'll tell, some people to find this f, x, y, and some people define this f, y, x, and we'll compare and say, are these answers going to be the same? And if we can do this, 3, 4, 5 times, we maybe can convince ourselves or find a counterexample where they're not. Since this is just a video and there's not a lot of interaction here, I'm not going to do this. I'll just tell you what happens. In this class, they're all going to be the same. In fact, most of the time, they'll all be the same. These fxy and fyx. It doesn't matter what order you take these partial derivatives. But that's not always true. For us, it will be, but in general, it's not. In fact, there's a nice classification of certain types of functions where we say, okay, they're nice functions because these partial derivatives are the same as each other. This is not a Calc 3 course, though, and so we're not going to dig into the nitty-gritty details of all that. All you need to know is that really you only need to find 3 of these second-order partial derivatives, because if you find this fxx and fyy, then you just need to find one of these other two, and they'll be the same. So enjoy that. Hopefully that works out. I think it takes a little bit of practice to get used to finding these partial derivatives. Maybe if you want some practice, find the second order partial derivatives of these functions. Notice these ones are going to be kind of annoying because there's some product rule and chain rule that you'll have to do to find the second derivatives. So maybe go back to this one first and see if you can find the second order partial derivatives. Find the derivative of this with regard to x and with regard to y, and the derivative of this with regard to x and with regard to y. And you should find that these two things match up. So give it a shot. Try it out. hopefully that works out nicely for you. Outside of that, I think there's plenty of examples in the text that you can jump into and look at this. But typically, once we figure out how these variables interact with each other, this stuff won't be too bad. Let me know if you got any questions, but that's all I've got. Thanks for watching all these videos all semester long. We'll be in touch, obviously, through discussions and email and stuff as you kind of gear into the end of the semester. But that's our last time that I'll be talking at you over video. So congratulations on making it all the way through this stuff. All right, thanks. Bye.